Okay, so acoustics in speech science starts with talking about speech in terms of acoustics, where acoustics is then a part of physics. So that's part of physics that deals with all kinds of things about sound, how it's produced, how you control it, how it's transmitted, how it gets received. The subfield of acoustics called bioacoustics refers to sound production by animals, so things like birdsong, barking by dogs, songs by whales, that sort of stuff. Speech acoustics is the study of speech production by humans, and we actually know quite a bit about how humans produce and perceive speech. So this lecture will have an overview of basic physics concepts. There are quite a few concepts in the chapter, but I think most of them are not directly relevant to our understanding of speech at this level. So I'm going to talk about the important ones here, and these will be the ones that we are going to focus on as part of this first unit. So we have some terms for the physical description of an object. One is mass, the amount of matter that's in an object. It's related to weight. One is the volume, the amount of three-dimensional space that gets occupied by a liquid or a solid or a gas. And then density, how much mass there is within the space of that volume. When we're dealing with speech, that object that we have a physical description of is a volume of air. Making things move in physics requires force. So force is any influence that causes an object to undergo a change in speed, direction, or in shape. More force can either move a bigger object, or more force can take a smaller object and move it faster. So for example, there's a measure called horsepower that's used in describing engines of cars, and the bigger that number is, the faster that car can be moved, more or less. Speed is the distance something travels over a given unit of time. In our case, dealing with speech, we're going to often talk about centimeters of distance traveled in a number of seconds. Momentum is the mass of an object times its velocity, which is basically the same thing as speed. Velocity is just speed in a particular direction. If we have an object that's not moving, it has no momentum. Inertia is the resistance of an object to a change in its state of motion or its state of being at rest. So you may have heard a body in motion stays in motion, a body at rest stays in rest. If something isn't moving, it takes force to move it. If something is moving, it takes force to stop it from moving or to change how it moves. Elasticity is the property of a material that returns it to its original shape after it's been deformed by an external force. So if you squish something, if it's elastic, it will bounce back. If it's not elastic, it will stay squished. So why do we care about these concepts? We have force that's applied to air to move air molecules. So for example, there's expiration during respiration that's forcing air to leave your lungs, and that is going to be the force that provides energy for speech. We have a displacement wave of air molecules that moves at the speed of sound, which is approximately 34,400 centimeters per second. This varies with temperature, but we'll take that 34,400 as our standard measure for speed of sound for this class. The amount of displacement of those air molecules in a displacement wave is affected by inertia as it travels over a distance. So there's less displacement the farther away you get from the source of the displacement. So sounds get quieter as they travel through the air. And the nature of an air mass in terms of elasticity causes displacement of air molecules from sound to happen in all directions, so that sound radiates away from a sound source in a sphere. So, for example, if I were doing this lecture in a classroom and I turned around and faced away from you, you would still be able to hear me. The sound would radiate in all directions out of my mouth as I speak, and one of those directions would be, back behind my head where everybody would be sitting. Our next concept relates to the amount of displacement of an object. So in our case, the amount of displacement of a bunch of air molecules that make up a sound wave. The concept of work is an amount of force that's exerted over a total amount of distance. So not just a single application of force, but force exerted over a stretch. Energy is the term for the ability to do work, and there are two different kinds of energy. One is kinetic energy, the energy of an object that's in motion. So a moving object hits something, it will try to push that thing it hits. There's also potential energy, stored energy that can result in movement. So if I hold something up in the air, it has potential energy due to gravity. If I let go of that thing, it will fall because of the force applied by gravity. Power is the term for the rate of work done or energy that is used over a period of time. Intensity is that measure of power per unit of area. So when you break that all down, that basically amounts to how much force is applied over a particular area. Pressure is force acting perpendicularly, so in a specific direction, on a surface area. This is usually measured in either pascals or in centimeters of water displaced in a manometer. That's a measure you would have talked about a little bit in the anatomy class when talking about pressures. So, in our case, the relevant pressure is sound waves that hit a person's eardrum or that hit a microphone to be recorded on a computer. The way those sound waves get generated is a little bit more complicated. We have expiration that moves air. We have phonation that converts that air movement into waves that can be heard by the ear. And those waves further get modified by the shape of the vocal tract to have distinct acoustic properties. The image on the right-hand side of this slide is an attempt at a visualization of what sound would be like. We have a tube that comes out of nowhere on the left side next to the guy's shoulder. Presumably that's creating airflow that hits that round thing that looks a little bit like a fan, whatever it is. Presumably that airflow causes vibration, and that vibration results in sound that radiates away from the fan-looking thing in waves. You can't actually see sound, but if you could, that's kind of what it would look like. Taking all these concepts together, we can think a little bit about how they might be applied to the process of speech. So, for example, after inspiration, I have a lung full of air. I have a type of energy there. Is that type of energy kinetic or potential? I have pressure of air inside the lungs. Is that pressure positive pressure? Is that pressure negative pressure? Is that pressure 0? And then a true or false question, is the speed of sound of that resulting speech going to depend on how full the lungs are? So to go back to question number 1, with a lung full of air, the type of energy that I have is potential energy. I've filled the lungs up, and that gives me an opportunity then to use that full lung volume of air to start to move things around. So that's potential energy. Once we've had inspiration and the lungs are all full, we have a bunch of extra air in there. That creates a positive air pressure inside the lungs. Air is going to want to then flow out of the lungs if it can to equalize the pressure and get it back down to atmospheric pressure, which we take to be 0. And then speed of sound, depending on how full the lungs are. Speed of sound depends on temperature and otherwise doesn't change. The thing that's going to be affected by how full the lungs are is either how much pressure that air in the lungs generates, or perhaps the airflow of the air. Very full lungs, the air will want to vacate very quickly, so the airflow will be higher, but the speed of sound won't be affected. What that additional pressure would affect in terms of sound would be how loud it is, would be its amplitude, would be the amount of displacement.